Is it possible to identify the events that shape the surface of the planet Mars? A planet of vast but unrecognized landscapes. Vista after vista, eluding every attempt to explain them. Scientists labor to solve the mysteries through textbook theory. But if, as we have claimed, the cause was electrical, they will never get the expected answers. Many details of a new interpretation come from laboratory experiments with electric discharge. But how far can this new interpretation take us toward an understanding of Martian history? One advantage of the electrical perspective is that its every implication can be tested against massive layers of evidence now available, including wide-ranging experiments with electric arcs. If, as we've proposed, Mars was immersed in hemispheric discharge, the planet can be viewed as a laboratory in space for testing the electrical hypothesis. As seen in lightning displays, electric arcs exhibit dendritic branching, called Lichtenberg patterns. These look very much like the dendritic erosion created by flowing water. And electric arcs exploding across a surface can produce sinuous channels that also resemble fluid erosion. But there are differences. In electric discharge to a solid surface, the electron pathways frequently create dark spotting, or chains of craters, running along the channel floors or close by. The presence of crater concentrations in relation to surface channels offers a fundamental test of the electrical hypothesis. In electric experiments, we also see coronal streamers radiating perpendicularly from the primary discharge channel. Both the cratering and the coronal discharge are keys to a new understanding of the Martian surface. Did electric arcs cut the great channels on Mars? Nergal Vallis is some 3 miles or more in width and 250 miles in length. Yes, it did look like a dry riverbed when first seen by the Mariner 9 mission in 1972. But the original confidence of planetary scientists soon gave way to doubts, then to contradiction. A river can take many twists and turns along its path, but its tributaries will not look like the blunt alcoves of Nergal Vallis. Martian channels exhibit the predictable features of an electric scar. Rotating cylindrical arcs, sputtering along the primary discharge path, produced scalloping of the channel walls, with sharp, angular projections that are inconsistent with fluid flow. The same process left overlapping craters and alcoves that make no sense in terms of familiar erosional patterns. We see virtually identical craters, alcoves, and sharply cut, stubby gouges along the Niti Vallis. Numerous other Martian rills underscore the same enigma, and the unanswered questions grow year by year. Planetary scientists identify depressions such as these as collapsed lava tubes. Lava tubes form as flowing molten rock cools and hardens at its surface, insulating the lava below so it continues to flow in a tube that eventually empties. When an empty lava tube collapses, the result will be an entrance to a lava tube cave. A good example is Barker's Cave in Australia. So a cave entrance is the first thing to look for on Mars. The second thing to look for is a rubble field created by a collapsing roof. And a third thing to look for is abundant outflow, since the emptying of a lava tube requires an outflow region. But in reviewing innumerable instances of claimed lava tube collapse on Mars, we find no cave entrance, no rubble field from a collapsed roof, and no outflow. The depressions stand alone, with literally nothing to support the theoretical interpretation. Like any fluid, lava flow follows topographical relief, always running downhill. The channels seen here change direction randomly, in apparent disregard for topography. They make 90-degree turns, unrelated to surface gradients. And they also cross over each other with no disturbance of either. These depressions cannot be collapsed lava tubes. But what are they? What you see here is not the planet Mars. It is a surface affected by a very high voltage but microamp current, creating a complex of gouges and craters. Again, in electrical terms, craters and channels are inseparable companions. In responding to the mysterious channels and depressions on Mars, many planetary scientists thought they saw spreading and fracturing. And indeed, evidence of fracturing is present on Mars, as seen here. Here there are no associated craters or crater chains, and the nature of the stresses acting on the surface is an open question. Planetary scientists think in the same terms when considering the region of Avernus Collis. They identify the channels as cracks or fractures. But why the concentrations of craters and crater chains? A rotating electric arc traveling across the surface can alternately sputter forward to produce linear chains of craters, or advance on a continuous path to cut channels as if by a router, with uniform depth and parallel sides. The question of crater formation on rocky planets and moons must be reopened. The impact explanation would mean it's only necessary to count craters in order to calculate the age of a surface. But electric discharge on a hemispheric scale could quickly create a surface that looks 1 billion years old to those counting craters. Plasma scientist Dr. C.J. Ransom of VimaSat Laboratories conducted a series of experiments with electric arcs. Electric discharge produced surface cratering patterns closely resembling those observed on planets and moons. Even the surface darkening and central bumps or mounds of so many craters on Mars were present in the laboratory experiment. Electric arcs can also produce cratering patterns that could never be produced by impact. Complex terracing of crater floors and crater walls are a common effect of a rotating electric arc or discharge streamer. Across the surface of Mars, we observe countless examples of exotic terracing. Impact theory was never able to resolve the mysteries. So-called bullseye craters, with a central crater inside a larger crater, are surprisingly common on Mars. Could this be a rare accident? That explanation is reduced to absurdity when two such craters are seen side by side. In fact, several bullseye craters appear within the same region of Mars. But an ionized discharge path of lightning does allow for subsequent discharge along the same path. The bullseye crater is a logical extension of the electric model. And when it comes to improbable events side by side, these two craters with central peaks each terminating in another crater will certainly never be explained by impact. Impacts do not create hexagonal craters. But look closely at this region of Mars, and you'll see several hexagons, an observed form taken by rotating plasma, as seen in the planet Saturn's electrified polar hexagon. In an extended discharge, systematic cratering, pitting, or etching can be the norm. That's why in industrial applications, electric discharge machining can achieve exceptionally dependable results. The microscopic pitting of electric discharge can give a consistent depth and a remarkably smooth surface, despite the fact that the surface is entirely constituted of craters or pits. The same effect can be observed on seemingly smooth surfaces in the northern hemisphere of Mars, surfaces that have been excavated miles deep. But look more closely with the help of recent high-rise images, and smooth surfaces are revealed to be nothing more than fields of small, densely packed craters. The baffling crater field seen here, like so many others on Mars, is a perfect counterpart to an electrically machined surface.